This is Dr. Sandeep Kumar, Assistant Professor, Ramjas College, Delhi University. Dear friends, welcome back to the lecture series on heterocyclic compound. So in the last lecture, we have discussed about heterocyclic compounds, their definition, why we are calling them heterocyclic compounds, and we discussed that because hetero means different and cyclic means cyclic ring. So any cyclic system which has different atom other than carbon are known as heterocyclic compounds. Then we discussed about the biological importance of heterocyclic compounds in different fields as well as in our daily life. Further, we discussed about the classification of heterocyclic compounds. In classification, we got to know that heterocyclic compounds are classified into two categories. The first is non-aromatic heterocyclic compound and the second is aromatic heterocyclic compounds. Thereafter, we discussed about the nomenclature of heterocyclic compounds. So in nomenclature, we got to know that the naming of any heterocyclic compounds depends on the three parameters. The first is stem. After the stem, we have to use a specific suffix, and before the stem, we have to use a specific prefix. So after the combination of these three components, we can do naming of any heterocyclic compounds. Thereafter, we discussed about the first heterocyclic compound, that is pyrrole. So in pyrrole, we discussed about the structure and aromatic nature of pyrrole. Further, synthesis of pyrrole by using different methods and its physical properties. Then we started with the chemical properties of pyrrole compound, and in chemical properties we started with electrophilic substitution reactions. So in electrophilic substitution reaction, we found two observations about pyrrole molecule, that the electrophilic substitution reaction takes place at C2 position of pyrrole. Further, the second observation was that pyrrole is more reactive than benzene for electrophilic substitution reaction and hence needs mild condition for the reaction. So today we are going to start one by one electrophilic substitution reaction by starting with the first example, that is halogenation reaction. So we can do halogenation by taking chlorine, bromine or iodine and pyrrole as the substrate. So when pyrrole react with N-chlorosuccinamide, it produces 2-chloropyrrole. So this is pyrrole molecule and it is reacting with N-chlorosuccinamide and producing 2-chloropyrrole. As I told you that the electrophilic substitution reaction takes place at C2 position in most of the cases. So that's why we are getting 2-chloropyrrole as the product. However, when we do chlorination in presence of thionyl chloride and by taking ether as the solvent at 0 degree Celsius, then also we get 2-chloropyrrole as the product. But if we do the reaction in excess amount of thionyl chloride by taking the same solvent system, then the chlorination takes place at every position of pyrrole and we will get per-chloro 2H pyrrole as the product. Further, bromination of pyrrole can be carried out by using different conditions. When we use N-bromosuccinamide as the reagent system, then we get 2-bromopyrrole as the product. However, when bromination is carried out in presence of bromine and acetic acid as the solvent system, then the bromination will take place at every position of pyrrole and we will get 2, 3, 4, 5 tetrabromopyrrole as the product. Further, we can do iodination on pyrrole as well. So, for the iodination, we have to use iodine as the reagent system and potassium iodide in presence of potassium iodide, we can do iodination and will get the final product as 2, 3, 4, 5 tetraiodo pyrrole. That is also known as iodole as their common name. Further, the second type of electrophilic substitution reaction on pyrrole can be carried out, that is nitration. But the limitation is that we cannot use traditional nitrating mixture to carry out the nitration, because the traditional nitrating mixture, that is concentrated H2SO4 and concentrated nitric acid, that leads to the complete decomposition of pyrrole. That's why we have to use some alternative for this method. So, pyrroles are nitrated using acetyl nitrate at low temperature, and that will yield the mixture of product. The product will be 2 nitropyrrole and 3 nitropyrrole. That means the nitration will take place at C2 position as well as C3 position of pyrrole. So, the reaction takes place in 2 steps. The first step is synthesis of acetyl nitrate. The acetyl nitrate is synthesized by reaction between nitric acid and acetic anhydride at -10 degrees Celsius. So, it produces acetyl nitrate as the product and along with acetic acid. Further, in the second step, this acetyl nitrate react with pyrrole to produce 2 nitropyrrole and 3 nitropyrrole as the mixture of products. Further, the third kind of reaction, that is electrophilic substitution reaction on pyrrole, is possible, that is sulfonation. But the limitation here is that we cannot use concentrated sulfuric acid in this case. When we use concentrated sulfuric acid, that leads to the polymerization of pyrrole. Therefore, we have to use some alternative method. The alternative method is that we can use pyridine sulfur trioxide complex at 100 degrees Celsius that produce pyrrole 2-sulfonic acid as the product. So, this is the reaction. When we do reaction of pyrrole with concentrated H2SO4 at room temperature, then we will get pyrrole 2-sulfonic acid in very low yield, and the rest of the reactant will get polymerized. So, that is why we have to use pyridine sulfur trioxide complex system. So, it produces the desired product, that is pyrrole 2-sulfonic acid in good yield. Further, we are going to discuss the Willers-Meyer-Hack reaction on pyrrole molecule. This is also the kind of electrophilic substitution reaction and is used for the introduction of formyl group on any aromatic system. So, we know that pyrrole is an aromatic system, and that is why we can do the Willers-Meyer-Hack reaction on pyrrole molecule. So, when Willers-Meyer-Hack reaction is carried out on pyrrole, then we will get the introduction of formyl group at C2 position and will get pyrrole 2-carboxaldehyde as the product. The reagent system in this reaction is used, that is phosphorus oxychloride and dimethyl NN-dimethyl formamide, that is used as the reagent as well as the solvent system. Followed by we have to use aqueous solution of sodium carbonate. So, the mechanism of this reaction can be understood that the reaction takes place in two steps, just like any other kind of electrophilic substitution reaction. So just like electrophilic substitution reaction, the first step is generation of electrophile. So in this case also we do generate the electrophile, and the electrophile in this case is NN dimethyl chloromethylene iminium cation, and that is generated from the reaction of DMF with phosphorus oxychloride. Then the reaction proceeds through the formation of an iminium salt intermediate, which upon hydrolysis yield the corresponding aldehyde as the final product. So the mechanism can be understood as I told you that the reaction takes place in two steps. So in the first step we are going to generate the electrophile, that is iminium cation, in this case that is NN dimethyl chloromethylene iminium cation. So this intermediate that is generated by reaction between phosphorus oxychloride and NN dimethyl formamide. So what is happening here, that the lone pair on nitrogen will shift between carbon and nitrogen, and the pi electrons of oxygen will do attack on phosphorus, and there will be elimination of chloride ion. So we will get this intermediate, and now we are having this imine like system. So on this imine like system we know very well that carbon is electrophilic in nature in case of imine, and chloride ion can act as nucleophile system. So it will attack on this electrophilic carbon and will generate this intermediate. Then the elimination of iminium cation will take place from this intermediate, and we will get our electrophilic intermediate system. On this electrophilic intermediate system, pyrrole will attack from the C2 position, and we will get this intermediate. Then the lone pair or on nitrogen will make feasible to the chloride ion to leave out, and we will get this imine like system. And further at the final, the hydrolysis of imine will produce the keto group, and in this case the keto group is aldehydic group, and the final product will be pyrrole 2-carboxaldehyde. The another method for the introduction of formyl group on pyrrole is Gattermann formylation. So Gattermann formylation is carried out in presence of zinc cyanide and hydrochloric acid. So this is another alternative method for the formylation of pyrrole to get pyrrole 2-carboxaldehyde as the final product. So the reaction takes place in two steps. In the first step there will be generation of electrophile that is generated by reaction between zinc cyanide and hydrochloric acid. So when zinc cyanide and hydrochloric acid react, they produce zinc chloride and hydrogen cyanide. Further, zinc chloride is reacted with hydrochloric acid and will produce a complex that is H positive ion and ZnCl3 negative ion. Further, this complex will react with hydrogen cyanide, and in this case the nitrogen of hydrogen cyanide will get protonated, and we will have a iminium cation like system, and this iminium cation like system is electrophilic in nature, and we know that pyrrole is having aromatic system that is pi electrons. So it will attack on this imine system and will produce amine, and further hydrolysis of amine will produce carbonyl compound that is basically the aldehyde group on pyrrole molecule. Further, just like any other aromatic system, the coupling reaction is also possible on pyrrole system. So when we do coupling reaction on pyrrole, the coupling takes place at C2 position and we will get azo compounds. So one thing about pyrrole is that it is even more reactive than the NN dimethyl aniline derivative of benzene, and due to high reactivity the coupling reaction take place very fast and we will get the azo compound, that is C2 substituted pyrrole derivative. In case the C2 position is already occupied, then the coupling takes place at C5 position, and if both C2 and C5 position are already occupied, then the coupling reaction takes place at C3 position of pyrrole. Further, Friedel-Crafts acylation and Friedel-Crafts alkylations are not easily feasible in case of pyrrole. So there are alternative method for the Friedel-Crafts acylation reaction. The alternative method is named as Hoban-Host acylation reaction. So in Hoban-Host acylation reaction, the reaction involve the reaction between pyrrole and nitrile in presence of hydrochloric acid, and that result the formation of 2-acyl pyrrole as the final product. So in this case the reaction takes place in two steps. The first step is reaction between nitrile compound and hydrochloric acid. So when we do reaction between these two components, the protonation of nitrogen takes place and we will get amine cation as the intermediate system, and on this amine system the pyrrole will attack from the C2 position and we will get this intermediate. Then deprotonation will take place and we get amine as the intermediate system, and the hydrolysis of amine will produce keto as the final product. So in this way we can do acylation reaction on pyrrole molecule by using Hoban-Host acylation method. Then we are going to discuss the basic character of pyrrole. The basic character of pyrrole is very interesting and we always do compare with the simple amine system. As we know, the basic nature of any kind of amine is due to the presence of this lone pair on nitrogen atom, and this lone pair on nitrogen atom is easily available for the protonation, and that's why it can get protonated, and that's why this all kind of amines are basic in nature. But the scenario is different in case of pyrrole. In case of pyrrole, this lone pair is not available for the protonation. In fact, this lone pair is contributing toward aromatic sextate. That's why pyrrole is aromatic in nature, because including this lone pair, the pyrrole has 6 pi electron system. So that's why pyrrole is considered as very weak base in comparison to other amine system. Then we are going to discuss about the acidic nature of pyrrole. So we can say that pyrrole is slightly acidic in nature, or it is weak, it has weak acidic character. How we can say this? Because when pyrrole is heated with solid potassium hydroxide, it forms potassiopyrrole, and that indicate that it has weak acidic character. And the acidic nature of pyrrole is mainly attributed to the fact that pyrrole anion is significantly more resonance stabilized than neutral pyrrole molecule, because in these resonance stabilized pyrrole anion molecules, there is no positive and negative charge separation that makes the structure destable. But in case of pyrrole anion, these 5 structures are of higher stability because they do not have any positive and negative charge separation. So that's why pyrrole has weak acidic character, and due to weak acidic nature, pyrrole react with Grignard reagent. We can see that it is reacting with methyl magnesium bromide, and that produce pyrolyl magnesium halide, and this pyrolyl magnesium halide can be used for different kind of organic reactions in organic chemistry field. So now we are going to discuss the reaction of potassiopyrrole molecule because of acidic nature of pyrrole. So as we see in case of potassiopyrrole molecule, that the electron density is distributed either at C2 position or C3 position. So that's why all kind of electrophilic substitution reaction on potassiopyrrole will take place at either C2 position or C3 position, or it will produce a mixture of product that will be C2 substituted or C3 substituted. So the first example of this from this category is Kolb-Schmitt reaction. So in this reaction, potassiopyrrole react with carbon dioxide under pressure to produce a mixture of 2 and 3 pyrrole carboxylic acids. So you can see the reaction here that potassiopyrrole is reacting with carbon dioxide under pressure followed by hydrolysis, and it is producing pyrrole 2 carboxylic acid and pyrrole 3 carboxylic acid. Further, as like other system, aromatic system, the Riemer-Tiemann reaction is very famous on aromatic system. So the same reaction is also feasible in case of potassiopyrrole molecule. So but the limitation is that in this case we get a side product, that is 3-chloropyridine. Basically, Riemer-Tiemann reaction is used for the introduction of formyl group on any aromatic system. So we will get the desired product as well in major amount, that is 2-pyrrole carboxyldehyde, but along with that we will also get a side product in minor amount, that is 3-chloropyridine. Now let me discuss the formation of this side product, that is 3-chloropyridine from potassiopyrrole. The reaction is also known as ring expansion reaction. Why we are calling it ring expansion? Because in this case the 5-member ring is basically converting into 6-member ring. So that's why there is kind of ring expansion from 5 to 6-member ring. So in this case what is happening, that chloroform in presence of sodium ethoxide will produce dichlorocarbene, and we know very well that dichlorocarbene is electrophilic in nature. So it will react with the double bond of potassiopyrrole and will produce a cyclopropane fused system, and this cyclopropane fused pyrrole system is highly unstable, and there will be shifting of electrons and breaking of sigma bonds will take place, and after elimination of potassium chloride it will change into 3-chloropyridine. That is happening basically in the Riemer-Tiemann reaction. Further, Friedel-Crafts alkylation is also possible on pyrrole molecule, but direct Friedel-Crafts alkylation is not kind of feasible in case of pyrrole, we do in direct alkylation on potassio-pyrrole molecule or pyrrole magnesium bromide molecule. So when we do reaction with pyrrole magnesium bromide in presence of methyl bromide, then the methylation will take place at C2 position and C3 position. So in this way we will get the mixture of product. Now let me discuss about the reduction of pyrrole molecule. So by using different condition, we can get different product in case of pyrrole. We can get partial reduced product as well as we can get complete reduced product as well. So when pyrrole is reduced with zinc and acetic acid, it forms 3-pyrroline, that is 2,5-dihydropyrrole. For the reduction with hydrogen iodide and red phosphorus yield pyrrolidine, that is tetrahydropyrrole. And the second method, we can get pyrrolidine directly by using hydrogenation method in presence of nickel as the catalyst at 473 Kelvin. So these are the two reactions in which pyrrole is reacting with zinc in presence of acetic acid. So it is producing 3-pyrroline as the product. This is kind of partial reduction of pyrrole, and when we do further reaction with hydrogen iodide in red phosphorus, it will produce pyrrolidine. And direct formation of pyrrolidine is also available when we do reaction with hydrogen in presence of nickel as the catalyst. So thank you very much for watching this.